Beep beep, baby. Beep beeping beep beep baby. Okay then. What the fuck we are?
There.
Right here. So let's do this shit. I'm gonna pull my glasses on. I'm gonna pull my pants on my dick. You know what I'm saying? And let's start. Yeah. So we are in the fucking linear algebra. I'ma do also fucking statistics, probability, and shit. But let me see how far I can go with this.
There it is. X is 0.
So yeah, because I was falling fucking asleep last time I was watching this. So I'll do. We'll watch it again, all right? Yeah, exactly. You just said it again.
I don't want to write down a big definition.
Yeah.
You can see what it is.
I can see.
There's column 1, there's column 2. I multiply by some numbers, and I add.
He adds.
That's a combination, a linear combination, and I want to make those numbers the right numbers to produce 0, 3. Okay. Now I want to draw a picture that represents what this is algebra. What's the geometry? What's the picture that goes with it?
Oh,
okay. So again, these vectors have 2 components, so I better draw a picture like that.
Mm-hmm.
So can I put down these columns? I'll draw these columns as they are, and then I'll do a combination of them. So the first column is over 2 and down 1, right? So there's the first column.
Mm-hmm.
The first column, column 1. It's the vector 2 minus 1. The second column is, let's see, I go over minus 1 is the first component and up 2. It's here. There's column 2. So this, again, you see what its components are. Its components are minus 1, 2. Good. That's this guy. Now, now I have to take a combination. What combination shall I take? Why not the right combination? What the hell? Okay. So what the combination I'm going to take is the right one to produce 0, 3, and then we'll see it happen in the picture. So the right combination is to take x as one of those and 2 of these. It's
Why?
because
Oh yeah, because we had a subtraction.
we already know that that's the right x and y.
Oh, we
so
already
why
know.
not take the correct combination here and see it happen? Okay, so how do I picture this linear combination? So I start with this vector. That's already here. So that's 1 of column 1. That's 1 times column 1.
1 time.
Right there. And now I want to add on. So I'm going to hook the next vector on to the front of the arrow. We'll start the next vector, and it'll go this way. So let's see. Can I do it right? If I added on one of these vectors, it would go left 1 and up 2. So it would go left 1 and up 2. So it would probably get us to there. Maybe I'll do dotted line for that. Okay? That's 1 of column 2 tucked on to the end. But I wanted to tuck on 2 of column 2. So that the second one will go up left.
You wanted to what?
Vectors, it would go left 1 and up 2. So it would go left 1 and up 2. So it would probably get us to there. Maybe I'll do dotted line for that. Okay? That's 1 of column 2 tucked on to the end. But I wanted to tuck on 2 of column 2. So that the second one will go up left 1 and up 2 also. It'll probably end there. And there's another one. So what I've put in here is 2 of column 2. Added on. And where did I end up?
0, 3.
What are the coordinates of this
Bitch. 0, 3.
result? What do I get when I take 1 of this plus 2 of that? I do get that, of course. There it is. There it is. X is 0, y is 3. That's B. That's the answer we wanted. And how do I do it? You see, I do it just like the first component, I have a 2 and a minus 2. That produces a 0.
Yep.
And in the second component, I have a minus 1 and a 4. They combine to give the 3. But look at this picture. So here's our key picture. I combine this column and this column to get, to get this guy. That was the B. That's the 0, 3. Okay. So that idea of linear combinations is crucial. And also, do we want to think about this question? Sure, why not? What are all the combinations? If I took, can I go back to x's and y's? This is a question for really, it's going to come up over and over, but why don't we see it once now? If I took all the x's and all the y's, all the combinations.
What is that, the span, or what the fuck?
What would be all the results?
Linear combinations?
And actually, the result would be that I could get any right-hand side at all.
Right.
The combinations of this and this would fill the whole plane.
The whole fucking plane.
You can tuck that away. We'll explore it further. But this idea of what linear combination gives B and what do all the linear combinations give, what are all the possible achievable right-hand sides B, that's going to be basic. Okay, can I move to 3 equations and 3 unknowns? Because
3 equations and 3 unknowns.
it's easy to
Make it 2D.
picture the 2 by 2
Yeah.
case. Let me do a 3 by 3 example.
Sure. Fool.
Okay, I'll sort of start it the same way, say maybe 2x minus y, and maybe I'll take no z's as a 0, and maybe I'm...
Why 2x? Because the other one was 2, was also 2?
And 3.
Yeah, right? Yeah,
Okay, I'll sort of start it the same way, say maybe 2x minus y, and maybe I'll take no z's as a 0, and maybe a minus x and a 2y, and maybe a minus z is a, let me make that a minus 1. And just for variety, let me take minus 3z, minus 3 y's. I should keep the y's in that line. And 4 z's is, say, 4. Okay. That's 3 equations. I should keep the y's in that line.
You did the Gaussian whatever elimination or what?
And 4 z's is, say, 4. Okay.
When you say, I don't think that you're just making that up in the moment, huh?
That's 3 equations. I'm in 3.
Or are you? Because you multiply this times 4, yeah, and then we get 0.
Dimensions, x, y,
I
z.
guess.
And I don't have a solution yet.
Okay.
So I want to understand the equations and then solve them.
Mm-hmm.
Okay. So how do you understand them? The row picture is one way. The column picture is another very important way. Just let's remember the matrix form here, because that's easy. The matrix form, what's our matrix A? Our matrix A is this right-hand side, the 2 and the minus 1 and the 0 from the first row, the minus 1 and the 2 and the minus 1 from the second row, the 0, the minus 3, and the 4 from the third row. So it's a 3 by 3 matrix. 3 equations, 3 unknowns. And what's our right-hand side? Of course, it's the vector 0, minus 1, 4. Okay. So that's the way, that's the shorthand to write out the 3 equations. But it's the picture that I'm looking for today. Okay.
You say shorthand, right?
Uh,
Yeah, we just translate it. We just transpose it. Or,
that's the shorthand to write out the 3 equations. But it's the picture that I'm looking for today. Okay. So the row picture. All right, so I'm in 3 dimensions, x, y, and z.
Oh, picture.
And I want to take those equations one at a time and make a picture of all the points that satisfy. Let's take equation number 2. If I make a picture of all the points that satisfy, all the x, y, z points that solve this equation, well, first of all, the origin is not one of them. X, y, z being 0, 0, 0 would not solve that equation. Well, first of all, the origin is not one of them. X, y, z being 0, 0, 0 would not solve that equation.
What equation, bro?
To satisfy, let's take equation number 2. If I make a picture of all the points that satisfy, all the x, y, z points that solve this equation, well, first of all, the origin is not one of them.
Why not? 0, 0, 0. Because, I don't know, why not?
X, y, z being 0, 0, 0 would not solve
But not only this one, right? Like, anyone.
that equation. So what are some points that do solve the equation? Let's see, maybe if x is 1, y and z could be 0.
Yeah. Is it? Is it true? 1. What the fuck?
That would work, right? So there's 1 point. I'm looking at this second equation here just to start with. Let's see. Also, I guess if z could be 1, x and y could be 0, so that would just go straight up that axis. And probably I want a third point here. Let me take x to be 0. Let's say x to be 0, z to be 0, then y would be minus a half, right? So there's a third point somewhere. Oh, my, okay. Let's see.
What happened, motherfucker?
I want to put in all the points that satisfy that equation. Do you know what that bunch of points will be?
No.
It's a plane. If we have a linear equation, then fortunately, the graph of the thing, the plot of all the points that solve it, are a plane. So these 3 points determine a plane, but your lecture is not Rembrandt, and the art is going to be the weak point here.
Oh, he's saying he's not a good drawer. Painter.
Your lecture is not Rembrandt, and the art is going to be the weak point here. So I'm just going to draw a plane, right? There's a plane somewhere. That's my plane.
What the fuck?
That plane is all the points that solves this guy.
Okay.
Then, what about this one?
We gotta plot just x and y, right?
2x minus y plus 0z. So z actually can be anything. Again, it's going to be another plane. Each row in a 3x3 problem gives us a plane in 3 dimensions.
Wait. What do you mean a plane in 3 dimensions? Shouldn't be a physical thing in 3D. So you're telling me that in a 3x3 we got a plane. So in a 2x2 we got a fucking line?
So this one is going to be some other plane. Maybe I'll try to draw it like this. And those 2 planes meet in a line. So if I have 2...
Yeah, that's what I'm talking about. That's what I'm fucking talking about. What is this?
2 equations, just the first 2 equations in 3 dimensions, those give me a line, the line where those 2 planes meet. And now the third guy is a third plane, and it goes somewhere. Okay, those three things meet in a point. Now, I don't know where that point is, frankly, but linear algebra will find it. The main point is that the three planes, because they're not parallel, they're not special, they do meet in one point, and that's the solution. But maybe you can see that this row picture is getting a little hard to see. The row picture was a cinch when we looked at two lines meeting. When we look at three planes meeting, it's not so clear, and in 4 dimensions, probably a little less clear. So, can I quit on the row picture? I'll quit on the row picture before I've successfully found the point where the three planes meet. All I really want to see is that the row picture consists of 3 planes, and if everything works right, 3 planes meet in one point, and that's a solution. Now, you can tell I prefer the column picture. Okay, so let me take the column picture. That's x times, so there were 2 x's in the first equation, minus 1 x's, and no x's in the third. It's just the first column of that. Mm-hmm. And how many y's are there? There's minus 1 in the first equation, 2 in the second, and maybe minus 3 in the third. Just the second column of my matrix. And z times no z's, minus 1 z's, and 4 z's. And it's those 3 columns, right, that I have to combine to produce the right-hand side, which is 0, minus 1, 4. Okay. So what have we got on this left-hand side? A linear combination. It's a linear combination now of 3 vectors, and they happen to be, each one is a 3-dimensional.
Wait. Oh. Yeah, I was thinking about it. Like, these numbers are just the same at the end.
Right? Vector. So we want to...
This column is the same at the end.
We want to know what combination of those 3 vectors produces that one. Shall I try to draw the column picture then? So since these vectors have 3 components, so it's some multiple. Let me draw in the first column as before. So x is 2 and y is minus 1. Maybe there's the first column. Y, the second column has maybe a minus 1 and a 2 in the y's and minus 3's, somewhere there possibly. Column 2.
Wait, what is that?
Is 2 and y is minus 1. Maybe there's the first column. Y, the second column has maybe a minus 1 and a 2 in the y's and minus 3's, somewhere there possibly.
Shit. Wow.
Column 2.
Yep.
And the third column has no
Z.
No 0, minus 1, 4.
I'm sorry. I mean, no 0.
So how shall I draw that? So nothing in this was the
right?
first component. The second
The fuck?
component was a minus 1, maybe up here.
Wait, what the fuck?
So how shall I draw that? So nothing
This is the first component.
in
Shit,
this
okay.
was the
Component.
first component. The second component was a minus 1.
So nothing here, minus 1, fucking here. Oh, here. What about the 4? This is so weird.
Maybe up
man.
here.
Are you sure?
That's column 3.
Oh,
that's
yeah.
That's the column
kinda crazy,
0,
though.
minus 1, and 4. This guy. So, again, what's my problem? What this equation is asking me to do is to combine these 3 vectors with the right combination to produce this one. Well, you can see what the right combination is, because in this special problem, specially chosen by the lecturer, that right-hand side that I'm trying to get is actually one of these columns. So I know how to get that one. So what's the solution? What combination will work?
Say that again.
Hand side that I'm trying to get is actually one of these columns. So I know how to get that one. So what's the solution? What combination will work? I just want one of these and none of these. So x should be 0, y should be 0, and z should be 1.
What? What are you talking about, bro?
Want one of these and none of these. So x
Oh, really?
should be 0, y should be 0, and z should
1.
be 1.
I mean, but that's not the only way to do it, right? Because I don't know, they can have different numbers, values,
Right-hand side that
right?
combination is. Because in this special problem, especially chosen by the lecturer, that right-hand side that I'm trying to get is actually one of these columns.
Yeah.
So I know how to get that one. So what's the solution? What combination
But that's
will
the
work?
only solution or one of the solutions?
I just want one of these and none of these. So x should be 0, y should be 0, and z should be 1. That's the combination. None of that, one of those is obviously the right one. So this column 3 is actually the same as B in this particular problem.
Bro.
I made it work that way just so we would get an answer, 0, 0, 1. So somehow,
Hold on.
that's the combination. None of that, one of those is obviously the right one. So this column 3 is actually the same as B in this particular problem.
This one, yeah.
I made it work that way just so we...
Cause come on, bro. Come on, brother.
would get an answer, 0, 0, 1. So somehow that's the point where those three planes met, and I couldn't see it before. Of course, I won't always be able to.
Okay.
To see it from the column picture either. It's the next lecture, actually, which is about elimination, which is the systematic way that everybody, every bit of software too,
Software. Computation.
production large-scale software would
Nice.
solve the equations. So the lecture that's coming up, if I was to add that to the syllabus, will be about how to find x, y, z in all cases.
Okay.
Can I just think
Yeah.
again, though, about the big picture.
Please.
By the big picture, I mean, let's keep this same matrix on the left, but imagine that we have a different right-hand side.
Right-hand side. You mean B,
Oh,
right?
let me take a different right-hand side. So I'll change that right-hand side to something that actually is also pretty special.
Oh, what?
Let me change it to, suppose if I add those first two columns, that would give me a 1 and a 1 and a minus.
And then you're gonna say C is a fucking 0, and there's just 1,
Minus
1.
3. There's a very special right-hand side.
Yeah.
I just cooked it up by adding this one to this one. Now, what's the solution with this new right-hand side? The solution with this new right-hand side is clear. Now I took one of these, and none of those. So actually it just changed around to this when I took this new right-hand side. Okay.
What a cool eraser,
So
huh?
in the row picture, I have 3 different planes. Three new planes meeting now at this point. In the column picture, I have the same 3 columns, but now I'm combining them to produce this guy. And it turned out that column 1 plus column 2, which would be somewhere there is the right column. One of this and one of this would give me the new B. Okay, so that's like we squeezed in an extra example. But now think about all B's, all right-hand sides. Can I solve these equations for every right-hand side? Can I ask that question? So that's the algebra question. Can I solve AX equal B for every B? Let me write that down. Can I solve AX equal B for every right-hand side B? I mean, is there a solution? And then, if there is,
Can I solve AX?
for every right-hand side B.
What do you mean?
I mean,
B?
is there a solution?
Is there a
And
solution?
then, if there is,
What is?
elimination will give me a way to find it.
Elimination.
I really wanted to ask, is there a solution for every right-hand side? So now, can I put that in different words? In this linear combination words? So in linear combination words, do the linear combinations of the columns fill 3-dimensional space? Every B means all the B's in 3-dimensional space. So, space.
Do the linear combination.
Every
All
B
the columns.
means all the B's in 3-dimensional space. So, do you see that I'm just asking the same question in different words? Solving AX, oh, that's very important. A times X, when I multiply a matrix by a vector,
Matrix by a vector.
I get a combination of the columns. I'll write that down in a moment. So that, you see, but in my column picture, that's really what I'm doing. I'm taking linear combinations of these 3 columns, and I'm trying to find B. And actually, the answer for this matrix will be yes. For this matrix, for this matrix A, for these columns, the answer is yes. This matrix is this matrix that I chose for an example.
What was your question, bro?
For this matrix, these 3 columns, and I'm trying to find B.
Yeah.
And actually, the answer for this matrix will be yes. For this matrix, for this matrix A, for these columns, the answer is Yes. This matrix is, this matrix that I chose for an example is a good matrix, a non-singular matrix, an invertible matrix. So those will be the matrices that we like best.
What is an invertible matrix? Come on, bro. So this chat is gonna use it to ask like shit, and this nigga gonna use it for problems. He's gonna review my problems.
There could be
My solutions to problems.
other, and we will see other matrices where the answer becomes no. Oh, actually, you can see when it would become no.
In the last one?
When could, what could go wrong? How could it go wrong that out of 3 columns and all their combinations,
I don't know.
when would I not be able to produce some B off here? When could it go wrong? Do you see that the combinations, let me say when it goes wrong. If these 3 columns all lie in the same plane, then their combinations will lie in that same plane.
What?
So when could it go wrong? Do you see that the combinations, let me say when it goes wrong. If these 3 columns all lie in the same plane,
The same plane. These 3 columns lie in the same plane.
then their combinations will lie in that same plane. So
Okay.
then we're in trouble. If the 3 columns of my matrix, if those 3 vectors happen to lie in the same plane, for example, if column 3 is just the sum of column 1 and column 2, I would be in trouble. That would be a matrix A where the answer would be no. Because the combinations, if column 3 is in the same plane as column 1 and 2, I don't get anything new from that. All the combinations are in the plane, and the only right-hand sides B that I could get would be the ones in that plane. So I could solve it for some right-hand sides when B is in the plane, but most right-hand sides would be out of the plane and unreachable. So that would be a singular case.
Singular
the matrix
case.
would be
That would be a singular case.
not invertible. There would not be a solution for every B.
What the fuck? Bro. Oh, my nigga. That was... Sure.
The answer would become no for that. Okay. I don't know. Shall we take just a little shot at thinking about 9 dimensions? Imagine that we have vectors with 9 components. Well, it's going to be hard to visualize those. I don't pretend to do it. But somehow, pretend you do. Pretend we have, if this was 9 equations in 9 unknowns, then we would have 9 columns, and each one would be a vector in nine dimensions. Imagine that we have vectors with 9 components. Well, it's going to be hard to visualize those. I don't pretend to do it. But somehow, pretend you do. Pretend we have, if this was 9 equations in 9 unknowns, then we would have 9 columns, and each one would be a vector in
9 components.
9-dimensional space.
9-dimensional space. But let me remember something. The dimension depends on the columns, right? Of the number of the columns.
And we would be looking at their linear combinations.
Okay.
So we'd be having the linear combinations of 9 vectors in 9-dimensional space, and we would be trying to find the combination that hit the correct right-hand side B. And we might also ask the question, can we always do it? Can we get every right-hand side B? And certainly it will depend on those 9 columns. Sometimes the answer will be yes. If I picked a random matrix, it would be yes, actually. If I used MATLAB and just used the random command, picked out a 9x9 matrix, I guarantee it would be good. It would be non-singular, it would be invertible, all beautiful.
Okay.
But if I choose those columns so that they're not independent, so that so that the 9th column is the same as the 8th column, then it contributes nothing new, and there would be right-hand sides B that I couldn't get. Can you sort of think about 9 vectors in 9-dimensional space and take their combinations? That's really the...
9 vectors, 9-dimensional space.
Can you sort of think about 9 vectors in 9-dimensional space and take their combinations? That's really the central thought that you get kind of used to in linear algebra, even though you can't really visualize it, you sort of think you can after a while. Those 9 columns and all their combinations may very well fill out the whole 9-dimensional space. But if the 9th column happened to be the same as the 8th column and gave nothing new...
Oh. So when 2 columns are the same... Wait. I don't know.
Then probably what it would fill out would be, I hesitate even to say this, it would be a sort of plane, an 8-dimensional plane inside 9-dimensional space.
8-dimensional plane?
And it's those 8-dimensional planes inside 9-dimensional space.
Oh my god. How can a plane be 8-dimensional space? I thought a plane was always 2D. 3D. Okay. Think about it, bro. Give me a good answer, all right?
That
Yep, scroll.
we have to work with eventually. For now, let's stay with the nice case where the matrices work. We can get every right-hand side B, and here we see how to do it with columns. Okay, there was one step that which I realized I was saying in words that I now want to write in letters, because I'm coming back to the matrix form of the equation. So let me write it here. The matrix form of my equation, of my system is some matrix A times some vector x equals some right-hand side B. Okay. So this is a multiplication, A times x, matrix times vector. And I just want to say, how do you multiply a matrix by a vector? Okay, so I'm just going to create a matrix. Let me take 2, 5, 1, 3. And let me, of my system is some matrix A times some vector x equals
Matrix vector.
some right-hand side B. Okay. So this is a multiplication, A times x, matrix times vector.
Yeah.
And I just want to say, how do you multiply a matrix by a vector?
Just do it, bro.
Okay, so I'm just going to create a matrix. Let me take 2, 5, 1, 3. And let me take a vector,
2 and 4.
x to be, say, 1 and 2. How do I multiply a matrix by a vector?
Just do it, bro. Oh, I remember rows and columns. Rows and columns.
Just think a little bit about matrix notation and how to do that multiplication. So let me say how I multiply a matrix by a vector.
2 times 1. 5
Actually,
times
there are
1.
2 ways to do it.
Really?
Let me tell you my favorite way.
Okay, hold on. System. Fuck, man. Matrix. Vector. What is B? It's just B, okay? So let's say we have
It's columns again. It's a column at a time. For me, that matrix, this
Tú también ya no era rows first, nigga. Okay.
matrix multiplication says I take 1 of that column and 2 of that column and add. So this is, the way I would think of it, is 1 of the first column and 2 of the second column, and let's just see what we get. So in the first component, I'm getting a 2 and a 10. I'm getting a 12 there. In the second, the way I would think of it, is 1 of the first column and 2 of the...
Oh, that's a way. Yep. And 2 of 5, 3.
the second column, and
But is that the same? Like, yeah, it's the same. No, it's not the same. It's not the same as starting with rows. Bum bum. Is it? No, it's not.
let's just see what we get. So in the first,
Really, bro? I didn't know it was just like that. Okay, so 1 times the first column plus 2 times second column, which is just
component, I'm getting a 2 and a 10. I'm getting a 12 there. In the second component, I'm getting a 1 and a 6. I'm getting a 7. So that matrix times that vector is 12, 7.
Yep.
Now, you could do that another way.
Rows and columns.
You could do it a row at a time.
Yeah, man.
You could do, and you would get this 12, and actually I pretty much did it here,
What do you mean?
this way. 2, I could take that row times my vector. This is all the time, this is the idea of a dot product. This vector,
Oh, dot product.
this way. 2, I could take that row times my vector. This is all the time, this is the idea of a dot product. This vector times this vector. 2 times 1 plus 5 times 2.
Oh. I thought it was like the whole row with the whole column. But it's not. So what if... Okay, that works with that. Oh, that, and then when we have another matrix that's different. It's a little bit different, but just like essentially the same shit. So then 1, dun, 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 3, 2, right? Yeah. Interesting. Okay.
2 is the 12. This vector times this vector.
Yeah.
1 times 1 plus 3 times 2 is
Yeah.
the 7.
Yeah.
So I can do it by rows, and in each row times my x is what I'll later call a dot product.
Dot product. Each row times what? By rows. Second way by rows. Which is 2, 1 plus 2, fucking 12, and then just, yeah. Beautiful. Say that
I
again.
can do it by rows, and in each row times my x is what I'll later call a dot product.
Times x is a dot product. Dot dot dot. Wanna go to the breast or bit? Okay, let me see.
But I also
Wait. My nigga, what the fuck? Let me see. Oh, this is about to finish. When this shit finishes, I'ma come. No, nigga. When this shit finishes, I'll go to the restroom. Okay. Not bathroom. Restroom.
like to see it by columns. I see this as a linear combination of the columns. So here's my point. A times x is a combination of the columns of A.
What the fuck is that? Is that a off? Combination off. That's beautiful. For
That's
real. It looks like Leo. Like Leo's zodiacal sign. Zodiac sign.
that's
Or is it
how
like
I.
the corchete, pinche corchete, like the corchus, el corchete, no corchete, el solfeo, whatever, in the music notation, right? You know what I mean?
Hope you'll think of A times x.
8
What?
times 6. What the fuck?
Of A.
Oh yeah, 8 times 6.
That's
Combinations of
that's
A.
how I hope you'll think of A times x.
Oh, it's a combination of columns of A. Let me write that down. It's a combination of columns of A.
When we need
We're
it.
combining the columns with X though. Right.
Right now we've got, with small ones, we can always do it in different ways, but later think of it that way.
Yeah.
Okay, so that's the picture for a 2x2 system.
Yeah.
And if the right-hand side B happened to be 12-7, then of course the correct solution would be 1-2.
Chicka.
Okay, so let me come back next time to a systematic way using elimination to find the solution, if there is one, to a system of any size, and find out, if elimination fails, find out when there isn't a solution. Okay, thanks.
Say that shit again.
Because solution, if there is one, to a systematic way using elimination to find the solution, if there is one, to a system of any size, and find out, if elimination fails, find out when there isn't a solution. Okay, thanks.
When there isn't a solution. All right. So y'all niggas wanna have like 2-hour chapters or just less under 1 hour or even less than 2 hours? Because I know y'all are so fucking excited about these chapters, these movies, because this is a movie. Donachelo Aprendiendo, puta tu madre. It's a whole movie, nigga. Ah! Okay. check the money. Alright, ya vengo ya.